interesting stuff are going to happen. All right, let's get started. Okay. So today what we're going to do is we're going to start a new section, which is about symmetries. We start with angular momentum, but we already have been using symmetries. I just haven't mentioned these set of words. Symmetry plays an important, very extremely important role in physics. But before getting to symmetry, the discussion of symmetry, I just want to finish what we had with statistics. And because last time I went through it really fast, I'm going to also try to connect it properly with the Fermi-Dirac and Bose-Einstein distributions. All right. So if there are any questions as we go along, ask. One thing that I would recommend, section 5.4. Uh-oh. What's going on? My cursor is not working. Here we go. Section 5.4 of Intro to Quantum Mechanics Griffith with an H, has a nice discussion of what I'm going over. All right, so review of lecture 20. We saw that we have distinguishable particles. We can have distinguishable particles. Those are, but in quantum mechanics, what is natural is bosons and fermions as indistinguishable particles. In general, we said if we are in 3 dimensions or higher, all indistinguishable particles are either bosons and fermions. But we had a talk by Frank Wilczek yesterday that he talked about 2 dimensions, 2 plus 1 dimensions, and how there are anyons, exotic particles, statistics. Do you guys see the evidence for 2 pi over third? Okay, anyway, if you went to the talk, okay. All right, now what we did last time was we considered n particles, and assuming these are free particles, they're non-interacting, assuming that the spectrum of single particles is E1, E2, blah, 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 and these are just integers. And they come with degeneracies D1, D2, and so on and so forth, right? The goal was to demonstrate how important it is, what the consequences of whether you have distinguishable particles, indistinguishable bosons and fermions, what the consequences are for statistics. And what statistics are we talking about? We have n particles. There's a total amount of energy. The total number of particles is fixed. The total amount of energy is fixed. They are non-interacting, so the energy is just distributed between them. So it's just partitions of integers. And the question is, if you pick a particle at random, what is the probability of finding energy? Right? That's what it is. All right. So we said that we counted the number of microstates with n particles in state En. So let me just write on the board again. I hate this board, but it's okay. So we're putting n1 particles in here, n2 particles in here, so on and so forth. The total amount should add up to a fixed amount E, and total number of particles. This means that the fact that I'm summing them, it means that there's no potential between them, they're free. The fact that I'm summing these means that the number of particles fixed. Good. By the way, this is not true about nature. Just to let you know. All right. We said that in equilibrium, there's a principle of physics at the world of this course. There's an equilibrium. We define equilibrium as in equilibrium, we said every microstate is equally as likely, right? So if we have a certain amount of energy E distributed in any particular way, any allowed microstate is equally likely. So if we know exactly what the total energy is and the total number of particles are, what the two are, what we have is we have a microcanonical ensemble of equally likely in which every allowed microstate is equally likely. It's just a density matrix which is with equal coefficients on the diagonal, right? All right. So for distinguishable particles, we did this calculation of this is the number of the number of configurations with microstates with N1 and state E1, N2 and state E2, and so on and so forth. This was the answer that we derived last time. So just a binomial distribution. These are just what you expect from degeneracies, right? Then for fermions, we found fermions and boson. What's special is that if you have n particle states, we saw in an example that if you have n particle states where the amount of energies are fixed, you always end up with a single particle, right? Because you either have to, single state, microstate. You either have to, in the absence of degeneracies, you either have to symmetrize or anti-symmetrize. So that cuts down on the number of allowed microstates. For fermions, it's even less because of exclusion principle. You can only occupy state once, right? Fermions do not share. Bosons are happy to share. All right, so here's what we found for fermions, and here's the expression we found for bosons. Are there any questions? I went through it really fast, and the chalkboard is horrible, so I don't know if it was readable. Are there any questions about this derivation? I can just at least symbolically repeat what I said. All right, so these are the countings. Now, what we're gonna do is we're gonna be in what we're interested in. I said it in advance that when the number of particles becomes large, when you do these calculations, you figure out that the vast majority of possibilities for Q of N1, N2, become. So there will be one of them. There will be one particular configuration just dominates. It becomes exponentially larger than all of the other ones. So you could just drop the other ones and ask about the most likely scenario, right? Most likely distribution. So that's what we're going to be after. Most likely configuration. And I will make this quantifiable when I say that, well, you could actually do the calculation for yourself. You could just put these expressions on a computer and just look at large N and see how this distribution is going to go. But I'm going to also teach you about the Stirling approximation, where you could analytically approximate this. You don't need a large computer for doing this. All right. So how do we find a most likely configuration? What we're after is we would like to find the maximum of these functions, Q, N1, N2, N, blah, 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 as we vary N's, keeping the total N and the total energy fixed, right? Is that clear? So we're keeping the total N and total energy fixed, and then we're varying N1 to N's, and the question is maximize with respect to that. The way we do this is using the method of Lagrange multipliers. In this particular case, in anticipation of the fact that we're going to get exponentials, we are going to be, because Q is a positive number, if I want to maximize it, I can just maximize log of Q, right? All right, so we're going to be working with log of Q, ln of Q. How do you do Lagrange multipliers? You add, for every constraint, you add a coefficient, Lagrange multiplier, and you construct this function. So you have two constraints. The total number of particles conserved, the total energy is fixed. So you add two such coefficients with parameters that I'm calling alpha and beta. We're going to keep track of this, right? You achieve that according to the Lagrange multiplier method, you find your maximization modulo these two constraints when, by setting the derivative of gn respect to nn equal to 0, g respect to nn equal to 0, all nn, right? All of them. G with respect to alpha equal to 0, g respect to beta equal to 0. Is this familiar from calculus? It's called Lagrange multiplier method. You could read up on it if you don't recall on Wikipedia or your calculus courses, right? It's just the way if you have a regular function you want to extremise, you would just take derivatives with respect to all the variables and set them equal to 0. If you want to do that in the presence of constraints, you do this. You add to your function for every constraint a function that is 0 when the constraint is satisfied with alpha and beta, and then you take the with respect to alpha and beta. It's a pretty simple thing to prove, but you guys should look it up. All right, so that's what we're going to be doing. Before doing that, of course, you see that you're going to be taking logarithm of a bunch of factorials, right? Let me tell you something very important in physics that you should definitely know. Maybe you already know it. First thing to know is this relation. If you have n factorial is defined for integers, right? Positive integers. There's a complex function called gamma function that is the same as n factorial. Gamma of n plus 1 is n factorial. So they take the same values for positive integer n's, but gamma could be analytically continued to the complex plane everywhere. So in particular, there is a meaningful, if you ever have to come up with a notion of what is the factorial of 3/2, that is gamma of 5/2. You haven't learned about analytic continuation, but for physicists, the practical thing to keep in mind is that this is what it is. And the reason for it is that what is n factorial? N factorial satisfies this property. That could be used as a definition. Now, gamma of z plus 1 satisfies z gamma z. All right, good. So that's what the gamma function is. But this way, I've actually told you what the gamma function is. Now, gamma function has bizarre behavior in the negative plane, poles, but doesn't matter. All right, so what is the story? Here is the Stirling approximation. When n is large, n factorial is well approximated by square root 2 pi n over e. What was the name of it? E was, what was it called? The name 2.78, blah, blah, blah. Log. What? No, it's not log response. It's that 2.78, blah, blah, blah number. Okay, it's just what we use to define logarithms. N over e to the power of n. Okay. All right. So this is an approximation. Of course, because of this relation, okay, you could write this approximation in terms of for z, some arbitrary number, and it takes the following for ln of z factorial, which really means gamma of z plus 1 is this expression. All right, for large z. So if you plot them, here's a plot of n factorial are the points, right? And gamma of n plus 1 is the gamma function, right? Of course, it matches everywhere. And then this is this approximation. You already see that for small n, right? They're already, these are n. Already for 3, they're pretty darn close. So as you go to high numbers, in quantum mechanics or in statistical physics, we're talking about an Avogadro number, 10 to the power of absurd, like 23 or something number of particles. So there's no way on Earth you could distinguish between the two. So you should be using it. That's why it's such a powerful approximation method. Good. It's fun to play with these approximations. It's an incredibly powerful approximation. Good. All right. So what are we going to do? Let's go case by case. Let's study this case by case. We're going to start with the distinguishable particles. Here's the Q that we had. We're going to take the logarithm of it, add to it alpha constraint 1, beta constraint 2. Constraint 1 is the number conservation, total number is fixed. Constraint of beta corresponds to the constraint that the total energy is fixed. Okay, keep track of those two things. This is some line of algebra you could follow. First is just like taking logarithm and adding and subtracting. Then in this step, I put an approximation. What I've used is I've used Stirling's approximation here, right? You see that I had ln of n factorial, so I got nn. Sorry, where did I? Ln of n factorial here. Wait. It's ln of z factorial is z log z minus z. Okay, so I'm taking the so this would be, yeah, I've split it already. I've split this already. So yeah, you just have to look at the you have to fill up this. I cannot do it on quickly. This is an equality. Just all I've done is that I've taken this expression. Every time I have ln of n factorial, some large factorial, I've used Stirling approximation. All right, so this is after Stirling approximation. What remains to be done is that you have to take derivative with respect to nn, set all n's and set them equal to 0, and take derivative with respect to alpha and beta and set them equal to 0. Derivative with respect to alpha and beta will just tell you about the constraint, right? Derivative with respect to nn will give you this equation. I recommend that you do the algebra for yourself. So do the algebra at home. You obtain the following expression. So this is the derivative that has to vanish. Therefore, ln of nn, bring it to this side. I have ln of dn minus alpha minus beta en. So this is the expression you end up with. Let me just get rid of this expression. This is, I don't want this for now. All right. So here's the result of my extremization. There's a couple of derivatives, partial derivatives if we take, right? This is the most likely distribution. Alpha and beta will be fixed in terms of the total energy and total n, but let's leave that for now. Okay, so this is the result of the extremization. It means that the most likely Q, most likely, you could just fill up for each nn, for each en, what is the corresponding nn, right? We do this for fermions, same business. The starting point is this counting. You first construct the Lagrange multiplier function. You do the Stirling approximation. You take derivatives. You get this expression, and this is what you obtain. Let me just put them next to each other. So both of them are proportional to dn. That's sort of obvious. That was expected, right? As a matter of fact, you will see that it's natural to ask about divide by degeneracies. When we define our distributions, we always divide by degeneracies. So you could ignore this dn for now. What this is, it says that the number of particles of energy En is exponentially suppressed in energy En. Right? That's what it says. What does this say? Well, it has a little bit of a funny form. The exponent is down here. Can you see what is interesting about this? What is nn? If I take nn and divide it by dn, what do I obtain? This is supposed to be a fermionic distribution. If I divide by dn, I'm talking about a single the number of states. Sorry, the number of fermions I expect in a single microstate. That cannot be larger than 1. Right? So look at the structure of it. It's 1 over, if you divide by dn, 1 plus a positive number. That's always less than 1. Right? That is, this plus is super crucial. Right? Now, you repeat the calculation for bosons. Again, you construct the G function, take derivatives. This derivative is a little bit more involved, but this is the result of your extremization. You find dn minus 1. I'll tell you in a little bit that you can ignore that minus 1, but I won't tell you. I'll ask you to go figure out why you can ignore this minus 1. Divided by e to the power of alpha plus beta en minus 1. So all that happened going from, for distinguishable particles, you've just found an exponential distribution. Right? Just an exponential distribution. The number of particles would decay exponentially with energy. For fermions, you found that the number of particles would be 1 over 1 plus an exponential growing in energy. For bosons, this is the structure of it. So first thing you notice is that this can be larger than 1. Right? Can you notice another thing about this? What is kind of suspicious about this expression? Well, it won't be zero energy, but it's plausible that there would be choices of alpha and beta such that you get in the denominator 1 minus 1 and you get infinity. Right? What does that mean? It means that the number of the most likely distribution is all the particles sit on top of each other in a single state. This was observed back in early days of quantum mechanics, 1930s. Well, I'm getting the dates wrong, right? Really early days of quantum mechanics. But this says that bosons, it's plausible that bosons, once you have a lot of them, you could arrange alpha and beta parameters so that all of them jump in the same state on top of each other. That has a name. It's called Bose-Einstein condensate. Right? And there was this physicist at MIT, Wolfgang Ketterle, I think. His background in physics was something. He had a PhD in physics in some field, and then as a postdoc, he decided to switch to experiments. And his goal was, let's find this. Let's find state of matter where bosons all sit on top of each other and form Bose-Einstein condensate. He with his collaborators managed to do it, and they got a Nobel Prize. It's a very exotic state of matter where all the bosons sit on top of each other and occupy a single state. Good? All right. Now let's talk a little bit about the significance of alpha and beta. So this was the expression we start with. Let's just do, as physicists, sanity, let's just check dimensionalities of these things, right? Q was what? It's a number, so it's dimensionless. Log of it is also a number, it's dimensionless. So this function is dimensionless. This is a number, so alpha is dimensionless. This is energy. So beta better have inverse frequency, inverse energy units, aka frequency. All right. If you take temperature and multiply it by this constant called Boltzmann constant, 1 over kBT has dimension frequency. So if you wish, kBT is Mr. Boltzmann gave you a constant of nature. So, and then every time you have beta, just rename it this way. Turns out that this T is the same T that we're discussing. It's temperature. It's the only meaning of temperature. I said it very quickly last time, but the definition of temperature I've given you should give you some trouble. Because based on the definition I gave you, there are systems that can have negative temperature. Think about that. There are systems with negative temperature. You use them all the time. Does anyone have a name for it? Well, they behave like negative temperature. Exactly. Population inversion. It has a name. What's the device that uses population inversion? Lasers. All lasers are based on quantum systems that if you try to associate temperature to them, based on the quantum mechanical notion of temperature, it would be negative temperature. So they laze as a verb. All right, anyway, so enough detours. Good. So what we're gonna do is, well, we use KBT to define beta. We could also use KBT to define another variable, mu of t. It's just a repackaging of alpha, right? This repackaging is convenient because you're going to see that what we're going to care about is alpha over beta. Okay, that's what's going to appear in the equation. Well, you have already seen it in a sense. So this is just a repackaging. This has a name. This is called chemical potential. If you've ever heard the word chemical potential, this is what it is. Minus alpha KBT. All right. So we did our calculations. Let's take most probable number of particles in a particular state with energy E and just basically mod out by degeneracies. Here's what you're going to get. If you mod out by degeneracy, this was my n of n. This is the maximized most likely scenario. This is what it becomes. I had minus beta alpha. Sorry, I had minus beta epsilon minus alpha, right? So I'm just going to factor beta out and put alpha over beta so that this becomes minus mu, right? This is minus chemical potential. So what form does it take? It takes the form of minus energy per particle minus mu chemical potential over KBT. This is called the Maxwell-Boltzmann distribution. This is something that was derived by Maxwell back in the days of quantum mechanics. And it described everything pretty well. We use it in astrophysics. We use it in everything, right? It's all over the place. Quantum mechanics was discovered when people saw a mismatch. Well, no, that's incorrect. Because there is a problem with Maxwell-Boltzmann distribution. It's called the ultraviolet catastrophe. That got resolved. I mean, then Planck came along and said, oh, there is a problem in this distribution. So maybe energies are quantized, blah, blah, blah. And then things changed. Yeah.
The distribution looks like the energy density, black body radiation.
That's what it is. Yeah. Black body, I mean, Maxwell-Boltzmann distribution for distinguishable particle is the energy distribution of black body radiation. What does it say? Well, what is black body radiation? You have an oven. I just didn't say the word black body radiation last time, but I just described it. You have an oven with a tiny hole. It's like a black body, right? You don't see anything. There's only one hole, and there are a bunch of particles. They're non-interacting. They're not talking to each other. You know the total energy of it, right? And the total number of particles fixed. There's a hole in there. So from time to time, a particle comes out. That hole does the job of, there's a bunch of particles that close my eyes that pick at random. Right? Now the question is, what is the expectation of probability? The number of particles, you just sit there and count, measure the energies and plot the number of particles you see and their energies. This is what we derived, and that's what black body radiation is. Right? The key assumption here is non-interacting. Particle number conservation, non-interacting, conservation of energy sanity. So in physics, energy conservation is going to be very important. We're going to talk about that, but number conservation is going to be awfully violated because of relativity. It's a low energy coincidence that number of particles conserved. Is it? Sorry, let me just do one little thing. What am I talking about when I say number of particles is not conserved in nature? You've heard about the phenomenon of pair creation out of vacuum, right? A pair of particle, antiparticle, can pop out of the vacuum. That means number of particles is not conserved. And that is a must once you take relativity into account. There's no way around it. But that's just for those of you guys who are interested. All right, so yeah.
Just want to clarify that the Fermi-Dirac distribution equation on the bottom has e to the power of e minus, that's mu.
Mu,
correct?
yes. Yes. This? Oh. This, right? Mu. Yeah. So it's always this. The expression is all the exponents we found, the structure of them were E2. So everything was E2 minus, well, there was E2 minus alpha plus beta E, but they wrote as E2 minus beta alpha E plus alpha over beta. This was minus mu, right? And then this becomes E2 minus beta E. Good. All right. Any other questions? So this is the end of the last lecture. Rest of us. Good. All right, let's change gears. I'm going to start with the rest. If you look at the way we went about talking about quantum mechanics, we discussed two systems. We focused on two types of systems. We talked about spin systems through Stern-Gerlach experiment, right? Physics and experimental science. And the other system we talked about was free particle, a particle, right? In both cases, the way I argued for the Hilbert space, even or the way I basically constructed the Hilbert space without telling you guys was secretly using symmetries. The Stern-Gerlach, I'm just telling you an afterthought, right? Stern-Gerlach, what did I do? I was talking about measuring Sx, Sz, right? And those transformations. It's all about how they don't commute. But what is it that I'm doing in my lab? I'm rotating the experiment, right? I had some sort of magnetic field that was measuring some Sz, right? And I rotated this. The assumption was that when you rotate this, the rotation is a symmetry. We'll talk about what it means, right? I just rotated my experiment in different ways. So the symmetry over there was rotation. When I was talking about the free particle propagating in space, I constructed everything, the x hat and p hat operators, from translations, right? I constructed p hat operator from translations in space. That was a symmetry. I didn't tell you that, but it was a symmetry. How did I construct the Hamiltonian? Same thing. Translations in time. Hamiltonian was the generator of translation in time. Momentum was the generator of translation in space, right? This is a basic principle. Symmetries of your system tell us about how to think of the Hilbert space. We're going to build towards that, but in this gradual, right? I don't want to throw you inside representation theory, but what I'm going to do is we're going to first spend the remainder of the course. There are two parts to it. First, we're going to beat up in detail another symmetry of nature that you know. We already talked about it, rotations, right? We just touched upon it and we did not get into details. We're going to do that properly. Once, by the time that I'm done explaining, we're done going through that discussion of angular momentum and rotations, because the generator of rotation is angular momentum. Once we're done with that, then I can take a step away and say, okay, quantum mechanics is all about symmetries. We're going to discuss that as the last section, of course. Right? All right. I'm going to try to teach it the way I wish I was taught. But it might be a little bit abstract, but at least it helps me, hopefully you guys as well. Remember, so please do ask questions. I think the presentation should be logically sound. Remember the Stern-Gerlach experiment and the silver atoms. We had a measurement apparatus that we were rotating. We were rotating. So we wanted to measure, say, SZ. There was some sort of magnetic field in a direction, and then the silver atoms were going either up or down. I don't know why I drew it this way. They were going up or down, depending on it being up and down. And then I said, well, you could rotate this, your measurement device, and then we're going to say the rotation of the measurement device is measuring some other observable Sx and Sy. It was kind of a puzzle that was always coming at this +1, -1, but that's what it was. So what's the abstraction? We said the state of the silver atoms, the spin of the silver atom is your classical thing that you have in mind. In quantum mechanics, we said we're going to describe that with a vector in an auxiliary space. So think of quantum mechanics or the theory as a map from what you see in measurements to some auxiliary vector space called Hilbert space. The way we build a theory is I'm constructing an experiment here. First, I use the map to say what I've prepared. What is it? What's the description of it in this auxiliary Hilbert space? Then I use the laws of quantum mechanics and calculate a bunch of things. Then I come back and say, okay, those calculations have predictions for me in my experiment. So abstractly speaking, what we're doing in quantum mechanics is that we're constructing a map from our reality that we see to a Hilbert space. We do our evolution, all sorts of things in the Hilbert space, bring it back. Okay. Now, in my physical space, what I'm doing is I'm saying rotate your device. That's something I could do. Rotation of the device should have an analog in the Hilbert space. Whatever I can do in the physical reality should be described by some operation in the Hilbert space, right? We're going to use the word representation. All operations I can do to my physical system should be represented in the Hilbert space. Here means by matrix, right? Because we said that the Hilbert space we're dealing with were complex vector spaces, so they will be represented by matrices. Good. When I rotate the silver atoms, I did not really explain it this way, but what I'm doing is I'm applying a unitary to my state. All right. What does it say? It says that there's this classical world that I have, and then there's a quantum mechanical description of it. Every physical operation should be described by an operator in the Hilbert space, a matrix. Right? If it's a finite dimensional thing, it's just a matrix. Is everyone with me? Is that good? What is important is in classical physics, in my classical world, I could do measurements. Classically, measurements are readouts. I can read property 1. It's like a particle has a bunch of labels on it. I remove the labels, look at them, put them back. In my classical world, naively, these operations of reading the labels commute, right? Like I could do them in whatever order I want because I'm not changing the thing. But we said the representation of measurement in quantum mechanics is a bunch of projection operators that do not commute, right? So this is what Bell's theorem ruled out. Bell's theorem said that if you mapped your measurement business to some theory here that's not quantum mechanics and still treats measurements as readouts, it's inconsistent. You have to have an inequality that we see a violation of. But in my physical classical world, I also have operations that do not commute. Rotation, we're going to say that in a second. And those should also be represented by some operators in the Hilbert space that do not commute, of course. There will be unitaries. All right? But I want you to think about this. Whatever I can do in my experiment, this ladybug. whatever I can do in my experiment, whatever my experimentalists can do, they come to me and say, okay, model this. In quantum mechanics, that's what this map is. Fred? Is that clear? All right, let's talk about rotation. So for a bit, we're gonna talk about classical physics, what I can do in the lab. Let's talk about rotations in R3. Imagine you have a vector, x, y, z. When you're rotating it, you're applying a matrix on this x, y, z this way. What is special about rotations is that the length of the vector is unchanged, right? The length of the vector squared is this. So R acts on this guy. The action of the inverse on this guy is R transpose. So rotations correspond to orthogonal matrices. Orthogonal matrices are matrices that with the following property: R transpose R equal R, R transpose equal to identity, right? So for example, if you have a brick that's like asymmetric like that, a rotation by z-axis around the z-axis, about the z-axis, by angle pi over 2 would be described this way. Good. Let's use the notation of rz of pi over 2 this way. So you already see something. You already see that you could have guessed quantum mechanics from the onset, some features of quantum mechanics from the onset. In the classical world, when we have phenomena that are non-commuting, I'm gonna say that in a second. We use matrices. That's why we use matrices to describe them. In quantum mechanics, more things become non-commuting. Sorry, non-commuting. So we're still gonna use matrices. The magic at the level of one particle space was that how do you go from real vectors to complex vectors that we talked about, right? That was interference. All right. So before talking about failure of commutations, let me just tell you a little bit more about rotations to make sure we're all on the same page. The way that we would describe rotation around the z-axis by angle phi would be this way. The z component of the vector is unchanged. The x and y components will be multiplied by this matrix. Cosine phi, cosine phi minus sine phi sine. That's just rotations in the rotations about the z plane is rotation in the xy plane. When you rotate around the z plane, z vector. Rotation around the z vector, keeping z vector fixed, is in the xy plane. That's a coincidence of 3 dimensions, right? In higher dimensions, there's no such a thing. So in higher dimensions, when you describe rotations, you talk about the plane that it acts in, right? We say it acts in XY plane. But in 3 dimensions, all you have is 3D dimensions. So a rotation in XY keeps Z fixed. That's just a technicality. All right. Something that you will hear a lot in physics and will confuse the hell out of me and a lot of other people. There are 2 ways to think about transformations. In general, let's just talk about rotations. Active versus passive. Active is when you keep your coordinates fixed, z, x, y, and you physically rotate your object. So the break was like that, x, y, z. Now, this part of the break used to be on the x side. Now it's in the y side, orthogonal to y side. The passive picture, you don't do anything to your break. You just say, I'm going to rotate what I call x, y, z, this frame. Unless you're doing some fancier physics, avoid the passive picture. In this course, we're going to be using active picture, okay? That's just for simplicity. There is a lot about the passive picture that's important, but we're not talking about it, okay? We're going to talk about physical operation. We're always going to fix our coordinates and just move things around. All right, is this clear? So for example, how would you describe the rotation by angle theta that around the y-axis? So ry theta would be, it has to keep the y-axis fixed. So I have to put 1 here, right? There will be cosine theta, sine theta minus sine theta. Right? It's just, you might wonder about why I didn't put the minus sign here. Think about that. Yeah.
So this is just a matter of convenience.
For the purpose of this course, it's a matter of convenience, but there's a large, bigger story to tell. In general, yeah.
Just clarifying, what's a 3 by 3 and 0?
Yes, yes. So whatever I don't write is zero. So we'll be using the active picture, yeah.
For the entire dimensions, is it that you don't have a notion of axes or is that more than one?
No, you cannot label a rotation in the XY plane, you cannot label by one plane, one vector.
It's
That's-
more than one, that's fixed.
Sorry, I lied. A rotation in the XY plane, you cannot, you can still label by vector, but not this one. You can't say, like here I could say a rotation in the XY plane. I can write it this way, but I mean 3 dimensions I could put Z. What is not rotated, right? In higher dimensions, I can't say what is not rotated because there are a couple of them. All right. What do I mean when I say rotations do not commute? Well, just look at this. If you break, rotated by pi over 2, fixed around the z-axis, then, oh, this is such a bad quality picture. Rotated around the z-axis by pi over 2, followed by rotation by around x-axis by pi over 2. Now do it in the opposite order. You don't end up on the same thing. If you find this mind-boggling, go through it. And that is actually, these matrices precisely do that. Just multiply, check this by multiplying matrices. So what did we have? In our classical world, we had a set of transformations that were non-commuting, and we use matrices to model them. In quantum mechanics, we had a larger set of things that were non-commuting. So we had to extend everything. Talk about measurements for non-commuting. So we had to associate to measurements also matrices. The extra step was this I, right? There was interference. So here, all these matrices are real numbers. A vector is a real number, just coordinates of it. Right? It's real. So the matrices are real. In quantum mechanics, because of that stupid I and interference, we're dealing with complex vectors. So these were complex matrices. These will be complex matrices. Okay. So when you do this operation to your quantum system, each such a matrix will be represented on the Hilbert space using a complex matrix, which tells you what you have done to your kit. Right? That's the word representation. That's why every physicist has been doing what mathematicians call representation theory, but a lot of them don't know it. All right? Good. Let's talk infinitesimal rotations. Let me pause here. Are there any questions? It's very important that you realize that the rotations do not commute. That's crucial. Yeah.
Rotations that
The same as?
symmetry broken. Like,
No. Let symmetry breaking. I'm not sure what. I'm not sure if I understood your question, but symmetry breaking is a little bit of a different phenomenon. Good. Yeah.
is there such thing as rotations of the
Okay. What is a rotation? If you come from Mars or Martians and I want to describe rotations to you, how do I describe it? You've never seen 3 dimensions. You want to describe 5-dimensional rotations. You say it's a linear transformation of the matrix that keeps its length. That's what it is. Right? What's your question? In 1 dimension. What are the transformations in one dimension that will keep the length of a vector. So what is a one-dimensional vector? Just an arrow like this. Sorry. Yeah, there are only two transformations: identity and -1. It's a group Z2. Okay, good. Any other questions? So let me, I can, no, I'll answer this. All right, infinitesimal rotations. Infinitesimal rotations are when you say my cosine is some small value, epsilon, these are epsilons. And then you're going to expand these, Taylor expand them in small epsilon, right? So cosine is, expansion of cosine is 1 over epsilon over 2, sine is just epsilon, right? We're going to expand them to second order. So this is rotation around the z-axis by epsilon up to order O epsilon cube means that I'm dropping all terms at order epsilon cube and above. Right? So these are what they are. These are infinitesimal rotations. You see where I'm going, right? Previously, I argued for momentum as the generator of an infinitesimal translation. And H bar actually popped up there. And I told you that there are two H bars that pop up. When I did that to spatial translation, I got an H bar. When I did that in time translation, I got another H bar. And then I said they have to be the same. Here, we're going to do the same thing. We're going to expand this to the first order. Some operator and some H bar will come up. It's the same thing. Same H bar as before. There's only one H bar in quantum mechanics. All right, so this is classical calculation. This is classical physics, right? These are real numbers. Oh, and I forgot to finish this line. Anyway, I'll finish it. So calculate the commutator. I can write a commutator because these are matrices, right? This is what it is. You could show that the commutator of rotation by epsilon around x and rotation by y, infinitesimal rotation around x and y, is equivalent to a rotation around the z-axis by angle epsilon squared minus identity. There's no answer. This is a good check. Is that right hand side clear? Or should I write it? So what is RZ epsilon squared? RZ epsilon squared will be RZ epsilon squared. So this is going to be what? 0, 1, 1, 1, 1. 1, 0, 0, 0, 0. This would be 1 minus epsilon squared over 2. 1 minus epsilon squared over 2 minus epsilon squared. Good. So you see that if I subtract identity from this and drop all the terms that are epsilon cube and higher, I get the right hand side. So that equality is reasonable. Another thing that you know, I didn't even need to say it, is that rotation by angle 0 is just identity. You're not doing anything. So what is the right hand side here? Anyone wants to try it? Yeah. You got to be careful with the order. Yeah.
So normally you drop terms epsilon squared or do you like to keep them?
Well, let's keep them. There's no such a thing as allowed or not allowed. Let's keep them, and then we'll talk about the consequences of keeping them. The reason that we drop things is that we could, in some formulation, we could ignore them. Let's just, I have already done that calculation in my mind, so I know that we have to keep the epsilon squared term, and it will have consequences. Yeah. This term, sorry.
Yeah.
That means that any term that is order epsilon cube or higher. Oh yeah, this is some. When you write O some epsilon, it means that you can put in here any term that's order epsilon or higher order, epsilon squared, or epsilon 2, or epsilon to the power of 11,001. And computer science people use a little o as well, but we're never going to do that in physics. Typical physicist never uses it, doesn't even know what it is. Okay, any questions about this? So what am I gonna do next? I'm gonna try to represent these in the Hilbert space. Right? So what is that? And I had in my lab, I had a silver atom and some state of a silver atom that I associated to a vector complex, two-dimensional vector in the Hilbert space. Here I could do a rotation that I would describe by matrix R. That should be represented, quote unquote, right, by some matrix acting on alpha. Is that clear? Now, a quick question. This is 3 by 3 real matrix, orthogonal real matrix. What is the size of this matrix? What is it? Well, you know the size of it, but what it acts on? Sorry, yeah, it's two-dimensional. It's 2 by 2 and complex. Right? Good. So this is a 2 by 2 complex matrix. I've already forced you guys to use this without saying it. Remember when we were talking, a lot of you guys were confused about, or were asking questions about when we had something like this, or dot n, you know, I had s dot n. So here I had some n hat, and I was representing in the other side something like s dot n. We'll talk about it. All right. So rotations do not commute. Rotations, we model them using orthogonal matrices. Orthogonal matrices, in case you haven't heard the words, are the set of real matrices that satisfy this relation. Otherwise, you could say they preserve the length of a vector. Right? Orthogonal matrices are the set of matrices that preserve the length of a vector. Okay. So they keep the length of a vector invariant. So for example, if your physical lab is three-dimensional, this keeps the length of a three-dimensional real vector invariant. So these are 3 by 3 real matrices that are orthogonal. Orthogonal means that they satisfy this relation. Now, in quantum mechanics, we're going to represent R by some D of R. What kind of matrix it is, it depends on your Hilbert space. If I have a if my silver atom is a spin half particle, it has a Hilbert space represented by Hilbert space complex two-dimensional vector space. Rotations are going to be represented by 2 by 2 complex matrices. Right? What is the analog of this? The same way that this should keep the length of a vector fixed, this should keep the norm of a ket fixed. Such matrices are called unitary. U dagger U is equal to U dagger equal identity. That's what a unitary is, literally. So I already talked about unitary matrices. I introduced them. I gave you a definition. But it's just, it comes from the desire that we would like to keep the symmetry. It just keeps the length of a vector fixed. Because it's silly to change the length of a vector. Ket in the Hilbert space. Why is it silly? At the level of this course. There's no physics associated to multiplying this ket by 1200. Right? So For now, the slogan to keep in mind is that symmetry transformation is always going to be a unitary in the Hilbert space. There's a tiny caveat to what I'm saying. Wigner, Spain, very famous physicist, proved that theorem. We could easily prove it. I proved it in quantum field theory class. It's very straightforward. But it's very straightforward. No, I literally mean it. It's very straightforward. I could do it in this class as well. It's pretty straightforward. We might actually do it. I don't know if Sakurai has a proof of it, but a little bit later. By the way, let me say something arrogant. Quantum field theory is quantum mechanics done right, starting from symmetries. That's what it is. You just abandon all your principles as you say, I'm gonna start in pick your space-time dimension. 2 dimensions. What are my symmetries? Translation X, translation Y, rotations. Let's start with that and you do everything. That's the attitude. And then spinners come up, statistics, all sort of stuff come up. Just you take one step away. Anyway, all right, I'll shut up. Okay, now review of what we did previously. How am I doing on time actually? Oh, I'm doing well. Ha. So when we talked about space and time translations of space in space and time on the Hilbert space were represented by some unitaries that we expanded to the first order in epsilon. Now, because it's a unitary, there's an I here. Why do I put an I here? Because I want the generator of an infinitesimal transformation to be Hermitian. We did this on the board, right? If U dagger is equal to identity, G would be Hermitian if I pull an I out. Generator, yes. So every time, great. Thanks for asking. The word generator, maybe I haven't used it, but it comes from the following fact that if you have an infinitesimal translation, say, so what is infinitesimal translation? It's 1 minus, say, R Z epsilon. It's this. Oh, I think I should have said that. Sorry, thank you. I just assumed that I should have said that. Sorry. This is an infinitesimal translation. I can write it as identity minus epsilon 0 0 0 plus order epsilon squared, right? So this is what? This is identity minus epsilon, some matrix, which is 0, 0, 0, minus 1, 1, plus order epsilon squared. This part works really good. This is a generator of a translation. You take a translation transformation, expand it around 0 to the first order. That's what the generator is. If you have a representation of translation in the Hilbert space, you expand it to the first order, and the thing that sits next to epsilon is going to be called the generator.
Okay, so just that matrix.
That's whatever that matrix is.
Okay.
Or it doesn't have to be a matrix. It could be, like we saw an example of it. Okay, very good. How do I represent the translation? What's that generator of translation? Well, we saw that the generator of translation was p hat, right? Because when I did the translation, it was this. P hat over h bar was the generator of translation, right? Yeah, if you go back to what we did in the previous, previous lectures, what we did was we took the representation of translation in space, expanded exactly this way. Yeah, if you wish, this is a definition of what an infinitesimal generator is. Take it some transformation for epsilon amount and do it. Expand it, this coefficient generator. The general translation in the Hilbert space was momentum. In that case, epsilon was dx prime. The generator of time translation was Hamiltonian. That was dt prime. Notice that I had to pull out these h bars, right? It was just dimensional analysis. It just had to be there. And I argued that they're always the same. They're always the same H bar. Infinitesimal rotation around K axis by angle phi will have a generator as well in the Hilbert space that we're going to call J hat of K divided by the same H bar, epsilon is d phi. This is called the generator of rotation angular momentum. That's a name. What is JK in the case of silver atoms? As a matrix, what is it? It's a 2x2 complex matrix, which is Hermitian. Right? JK is a 2x2 complex matrix that's Hermitian. It was good? If I was, instead of silver atoms, I was dealing with some other particle, well, I'll say that later, that had a different spin. The generator would be a different dimensional. It would be still a Hermitian operator, but in some other dimension. This part of the course is about telling you what dimension precisely. All right, good. More generally, if you have a rotation around n hat, around some unit vector n hat, this is the three-dimensional description of it. You're rotating, keeping n hat fixed. The representation of that rotation by angle d phi, infinitesimal angle, would be identity minus I j hat dot n hat over h bar d phi. So based on this, can you tell me what the generator of in the Hilbert space, generator of x, y, and z rotations are for qubit? Pauli's. Exactly. That's it. That's where Pauli's came from. Now, a very, very important statement here. In classical physics, x hat and p hat, position and momentum, were physical quantities. For angular momentum, we said that the angular momentum is x hat cross, that's outer product of p hat. In quantum mechanics, that is incorrect. That's not what angular momentum is. Angular momentum is the generator of rotation, right? It's a general rotation in the Hilbert space. Why is this incorrect and that correct? Because you want to be able to rotate spin. Spin is not a vector in space, right? Spin, if you just viewed things as, rotations had to be some x dot cross p, there's no x and p for spin, right? So you would like a description of it that doesn't rely on anything like that. Of course, if you're talking about particular systems, then there is a way to derive the fact that for those particular systems, angular momentum will be related to x cross p. But even in that case, there's a subtlety. Can you guess what the subtlety is? When if I were to define x, so in quantum mechanics, I say x hat, p hat. If I were to define x L as x dot p, here I would have to write x hat cross p hat. But there's a problem with this. What's the problem? They don't commute. So here, like I could switch the order, I'll click on minus sign or something. But here, how am I going to represent them? That's not the definition of angular momentum. In quantum mechanics, spin comes out of the fact that we would like to represent rotations separately. Just a fundamental thing. Well, I haven't explained why spin comes out of that, but it's a fact. All right, so we have only a couple of minutes left. I only have 2 slides. Oh, a couple of slides, but. Rotations as matrices in space, 3-dimensional matrices, will satisfy the following 3 properties: identity, closure, inverse associativity. identity means that there is a transformation which does nothing. That's rotation by 0. And R times identity is R. Closure means any two rotation is another rotation. Said differently, any two successive rotations could be undone by a rotation, which would be R3 minus 1. Inverse says that every rotation could be undone. Associativity says that even though the order matters, but it doesn't matter how you multiply things. So R1 times R2 times. Associativity just means that this is sensible. You'll be surprised that there are things that are not associative. All right, all these properties must be preserved in the Hilbert space when you replace R by some representation of it. Right? Doing nothing in the Hilbert space should be represented by identity of the Hilbert space. And if you represent R1 by D of R1, this is a 2 by 2 complex matrices. Here we have 3 by 3 real matrices. Here you have 2 by 2 complex matrices, right? They should all satisfy these analogous properties, right? This is what the mathematician defines to be a representation. If you have all these, if you have a map from R to matrices of R, such that all these properties are satisfied, it's called representation. But physically, we use the word in English, representation, right? It makes sense. Yeah.
So you also need composition to maintain under representation.
That's second one.
Oh, okay.
Closure. That's what the representation is. Such a thing is called a group. If you have these properties, you have a group. Good. So if you hear the word group, so symmetries form groups. They always have these properties. All right. So now we talked about the fact that rotations in real space, three-dimensional space, don't commute. What are the commutation relations of angular momentum operator, the generator of rotation in the Hilbert space? We saw that. So how you do it? How do you do it? Just take a rotation around D. So what I've done on the board, on the slides, is actually let me write here. So this is. Let me erase this. This is the expansion of D of R of X of epsilon to the order to expanded to epsilon squared order, right? That's what it is. Similarly, this guy. So what I'm doing is I'm just calculating the commutator of two rotations around the x-axis and y-axis expanded to order epsilon squared. This is what I obtained. Now here comes the answer to your question. Why did I keep order epsilon squared? Because every jx comes with an epsilon. If I want to calculate the commutator of jx and jy from this expression, I have to take this term and this term. That's order epsilon squared. There's nothing to say about order epsilon. What is order epsilon capturing? It will be the commutator of jx and identity. But that's 0. That's boring. Right? So here it is. Jx, jy is the commutator is I h bar jz. Ji, jj is I h bar epsilon I j k k. Epsilon I j k is a totally antisymmetric tensor. You guys know what totally antisymmetric tensor is, right? Or look it up, just to make sure everybody is on the same page. So what is this? This is I h bar what? Minus jc. This keeps track of the order, because if you flip the order, you put your minus on, right? All right. So this is my last slide. I'm gonna say it's a summary. So this is where we are going, okay, in this part 3 of the course. We model spin half particle, silver atom, by the state of it by two-dimensional complex vector and the two-dimensional space. We're gonna show you that if the particle has spin J is always either half integer or integer, bosons, fermions, all that business. Then it will be represented by a 2J plus 1 dimensional complex vector. We'll prove that. We'll derive that, I think. So now, if you want to talk about rotations, the classical world is always, the world is always 3-dimensional. So rotations in my lab is always like orthogonal matrices. But when I try to represent it, if I'm rotating a spin half particle, the corresponding matrices would be 2x2 unitary, 2x2 unitary matrices, complex matrices. If I'm rotating in the lab a spin J particle, the only description of it is a 2J plus 1 times 2J plus 1 complex unitary matrix. This is to help you separate, you know, like what you do in your physical lab is this R. What is happening to your ket in the Hilbert space is D of R, and that depends on what the particle is. Good? All right. Are there any questions? Yeah.
Like you said that you keep one first order terms, 0 to 1. Second order term, they get that. And you keep on more and more terms.
So what is the question? I can keep the higher order terms. On the left hand side, I'll have epsilon cube. On the right hand side, I'll have to write an expression that has epsilon cube. That's order epsilon cube, right? Which would involve a couple of J's, right? Let me quickly give you the answer to that question. BCH, Baker, Campbell, Hospital. We discussed this in the class. That's if you kept the arbitrary order, that's what you're gonna get. Play with it. As a physicist, you should go through the pain of expanding Baker, Hausdorff, Campbell a couple of times in all sorts of different convenient or inconvenient bases to appreciate how useful this is. All right, any other questions? If not, thanks, guys.